Hello makers. Today we're going to finish the electrical assembly of our wind sensor system and go through the calibration procedure. At the end we'll have a fully functional wind speed and direction indicator as well as having reached a milestone in the project. Looking back at our original design requirements, we'll have all but the rain gauge and ambient light sensor completed and ready to move on from prototype to deployment. Drawing from experience gained during the calibration process for the wind sensors, the rain gauge will take longer to develop and test, so for now we'll plan to add that sensor after deployment. The ambient light sensor will be developed alongside with the power system, which is the next milestone now that the user interface is working and the core sensor suite is finished. To finish the wiring, I'm using 22 AWG security wire that is commonly used to wire home and business security systems. It's inexpensive and comes in a 500-foot roll with 4 conductors in the cable. I've used this cable for lots of different projects, and with 4 conductors, it can be used to wire stepper motors as well. When planning projects like this, I like to choose parts that can be reused or purchase extra that can be inventory for later projects. 22 AWG is just small enough to fit the drill holes in most circuit boards and just large enough to carry a useful amount of current for things like motors. One of my favorite parts of any build is the first time it looks and functions like a complete project. What was once a collection of spare systems now work together with purpose. Unfortunately, the best indoor wind source I have is a USB-powered desk fan, but it's well enough to test the mechanical movement, and with careful setup should provide a good enough calibration curve. During this initial testing, I noticed there was a critical value of airspeed that would start the anemometer rotating, as well as turn the wind vane in the direction of flow. It takes about 1 meter per second to get things moving, which is equivalent to the breeze that's generated by walking. Even though a lot of thought has gone into minimizing friction, there is still some present in the system. A little more concerning is the overall weight of the mechanical parts. As the mass increases, the rest inertia that has to be overcome grows, and with it friction. Future iterations will have to go through a weight reduction process, but for now we can establish a baseline of performance and plan for future improvements after deployment. The wind speed sensor outputs a signal that is proportional to its rotational speed. The signal increases when the anemometer spins faster. But how does that signal relate to the actual speed of the wind? Before we can use a sensor, it has to be calibrated against a known reference, or standard. Calibration is serious business in science and industry. In fact, there's an entire government agency devoted to standards, the National Institute of Standards and Technology, or NIST. Founded in 1901, NIST's mission is to promote U.S. innovation and industrial competitiveness by advancing measurement science, standards, and technology in ways that enhance economic security and improve our quality of life. NIST even has a standard reference material for peanut butter. Now, since a NIST traceable anemometer costs several $100s, I'm going to be using a handheld anemometer I found online for $15. Now, just as there are calibration standards, there are a standard calibration procedure. Anemometer calibration typically involves a wind tunnel and instrumentation, which we could build, but that entire process would be its own video series. At its core, to perform the calibration, we need to construct a graph of measured airspeed versus sensor output. If we can draw a straight line through the points plotted, then we can use the equation of a line to relate airspeed to sensor output. Let's go ahead and take a look at the calibration of our wind speed sensor. So earlier on, we took a series of measurements in terms of what the actual airspeed was from our handheld indicator and what the rotational sensor was giving to us. And to relate a sensor output signal to an actual wind speed, we're going to use a calibration curve and the equation of a best fit line. Here I'm using Microsoft Excel to plot the measured airspeed versus the sensor value recorded at that airspeed. The best fit line is produced by a technique called linear regression, and it's a technique used frequently to relate sensor data to a physical stimulus such as wind speed. Excel has a built-in function for this and displays not only the line, but also the equation of that line. The R squared value is a measure of how well that line fits the data. The closer to 1, the better. Using the equation of a line, y equals mx, and the slope of the line, we can calculate the wind speed given any sensor signal value. So what does this tell us about the limitations of our wind speed sensor? So first and foremost, we do have an area of nonlinearity just below 1.5 meters per second. And there are a couple things going on here. First of all, is going to be the calibration setup. The fan that I was using was a small desk fan, and as such, the amount of moving air is fairly focused to a small region, so it's not a large moving field that you would experience in deployment. Also, it was a limited power, so it was a little difficult to get things moving with that fan. The second aspect here is the design of the anemometer itself. There is a lot of weight still in the system, so we do have a lot of inertia and momentum to overcome. So essentially, when the wind speed is in this region down here, we're just not getting enough force to overcome the rest inertia and what little friction is left in the system, even though we have the thrust bearings and the other two vertical bearings keeping everything straight. So for wind speeds greater than 1.5 meters per second, we have a really good linear response here from our sensor. So this is what we're really looking for. So if I was to take this graph from 1.5 up to 2.2, this R square value would probably be closer to 0.99. So that would be a much better fit for the data. In this case, since we know that this is a mechanical issue and potentially a calibration issue, before deployment, what we'll want to do is come back and recalibrate this sensor either in the field or using a better fan system. But by and large, this data that we're collecting is useful for determining the suitability of putting up a wind turbine. So, for example, over the next year or so, if I want to collect wind speed data from my location, and there's a certain critical value of wind speed to produce useful power, with this data, we'll be able to determine, whether or not there'll be a good return on our investment. So for now, we're going to go ahead and stick with this calibration equation, and let's go ahead and get that plugged in and see what that looks like. In our previous video, we had roughed in some example code to make sure that communications between the AS5600 and Home Assistant were working properly. And now that calibration is finished, let's take a look at the finished code to see how all of this really works. Not much has changed since the last video in the top section of this. We still declare our objects. We have our separate sensors that'll be reported to Home Assistant. Polling conditions have stayed the same. Nothing here for setup, so it's not that big of a deal. But really, the meat and potatoes here happens in the override. And the problem statement is that we have a sensor that functions like a digital compass. It's going to report a number from 0 to 360. Now, how do we derive a rate of change information from that? And the solution is to have a known period of delay between two readings. Then we can calculate the elapsed time and then get a measurement that is in the time domain. So in this case, we're going to use the function called millis. And in Arduino, millis is used a lot to create timers and other timekeeping processes that's very lightweight because it's just a number. Well, it's a very big number in this case, considering it uses the long variable type. But we can call millis at the start of a process and then call millis at the end of a process, and we get a fairly accurate representation of the elapsed time between those two processes. Now, the reason this works is because the time that it takes for us to do this reading is on the order of microseconds, whereas our delay is in the millisecond category, so order of magnitude larger. So we can perform this reading and then perform this reading, and we know for fairly certain that we have 100 milliseconds between each one of those readings. In practice, I get about 103 milliseconds, so well within a margin of error here. Once we have these two readings and we have the elapsed time, we can then use that to calculate the rate at which the signal changes. Because essentially that's what we're interested in, is this rate of change. Now, sometimes I will leave old code in my program here just to kind of remind me of where I've been and what doesn't work. So in this case, I found that if the sensor starts rotating backwards, I would be getting erroneous data, and we saw that in the calibration. So after doing a little bit of additional research, I found pieces of a function that would do exactly what we needed to do. And this simply, we're just looking to see what the absolute difference between the two angles is, whether it's greater than or less than 1/2 of our unit circle. So in this case, since the sensor has 12 bits of resolution, a typical circle goes from 0 to 360 can then be represented from 0 to 4096. So we've got a lot of resolution available to us, and that makes the sensor more accurate. So in this case, we're simply saying, all right, the difference between reading 1 and reading 2, if it's less than or equal to 2048, the rotational speed is calculated as such. If the magnitude of the angles is greater, we're simply taking that difference and subtracting it from the whole. So in this case, 4096 minus the absolute value of that difference divided by our total time taken gives us a rate of change. And then finally, we want to apply our calibration curve. So when we did the y equals mx plus b to determine what the slope of that calibration line is, we take our rotational speed as calculated and divide it by our m value, since this would be y, and we rearrange this equation to give us our x. Finally, we're going to wait for another 100 milliseconds, and then we're going to activate our second bus on the I2C multiplexer, and we're going to read the wind direction. And of course, this one is much easier to get since the sensor is designed to do this natively. In this case, the only thing we need to worry about is to convert that 0 to 4096 value into an angle that we can then do something with. In this case, each degree is 0.087 tick. So in this case, we simply take our raw angle that we get and multiply that by 0.087 to give us a degree reading. And then that gets reported to Home Assistant. And again, a delay of 100 milliseconds just to let everything settle. And then this returns back to the top, where, because this is part of an override, will be called the next second later, since we have a 1000 millisecond delay between each time that loop runs. So really the difficult part, I think, in this was really figuring this out so that if the sensor rotates counterclockwise, we're not getting erroneous data. But this seems to be working fairly well right now. And in fact, we can go into our dashboard and we can see here that I've got a nice little circular gauge that gives us our wind direction. And currently I have a fan plugged in blowing on there to give me some data. So it looks about 4.5 meters per second. So that would be a fairly stiff breeze blowing in from east northeast. Home Assistant has a built-in statistics module, so we'll be able to prepare and display weather data in a variety of ways. Here's a 5-minute average dashboard card that took all of 20 seconds to create. From this milestone, we'll be branching out to work on the power system and move towards deployment. Back in video 1, I had made some assumptions about the power requirements for the sensors and the ESP8266. Let's take a measurement and see what the actual number is. I have a power meter that plugs in via USB and measures the voltage and current of whatever's plugged in. Very handy for testing devices that are powered by USB. Over the course of a minute, the power draw fluctuated between 50 and 70 milliamps, so better than expected. Thank you for joining us today, and if you have any questions about this project or Exploration Commons, don't hesitate to reach out. Thank you again, and take care.